Good morning, everybody. Today we have a Codeforces round. Again, as usual, this is Codeforces Global Round 16. At the end of this, I'll have solutions to all the problems I know how to solve, and this will be rated for me, so I'll be trying pretty hard to do well in it. So here we go. Let's jump right into the contest and start with problem A. If you got two distinct positive integers n and s, we want to find the maximum possible median of n integers such that the sum of elements is equal to s. So we can have the sum smaller than s, and we want m over 2 is n odd. Okay, what if n is even? What is the median? So the rounding up position. Okay, so the median of these arrays is 30, or is 40? 30. So the sixth thing to the third. Okay, so yeah, so the floor of the middle. Okay, so we want that many so we have, well, every element has to be positive, right? Oh, they can be non-negative. So you've got a bunch of zeros. One element, sum is 5. Okay. So you have 3 elements. In this case, you would want 0, 2, 3. Okay. Yes. So, into n equals this, and then s equals this. And then we want n equals n plus 1 over 2, and then sys out s over n. That should be the solution. Should we get this case wrong? Why did we get this wrong? 414. Well, what's the first? 522 147. So we get 2 elements that sum to 1. So s is, oh, is this s plus 2? Yeah, okay. 522044. Okay, looks good. Submit A. I'm a little slow on that, but that's fine. It's only a couple minutes. A binary string is a string that consists of characters 0 and 1. Let max of a binary string be the smallest digit that does not occur in the string. We got it, nice. A binary string s is given. You should cut it into any number of substrings such that each character is in exactly one substring. Wait, what? You should cut it into any number of substrings such that each character is in exactly one substring. Okay. Yeah, we know what a substring is. What's the minimal sum of mexes that this can be? So if you have a prefix of 1s, you can delete all of them. Otherwise, you include either everything, and then that will give you an answer of 2. Or if you have all zeros. Yeah, so if you have a bunch of 1s and a bunch of zeros, the answer is 1. If you have all 1s, the answer is 0. Otherwise, the answer is 2. So Boolean any zeros, Boolean any 1s. Do we care if we have any 1s? We care about any 0, 1. Yeah. for k or c in line. If c is equal to 0, then any zeros equals true. And for int I equals 1, less than n I plus plus. Okay, less than line.length. If line at I is equal to 0, or is equal to 1, and line at I minus 1 is equal to 0, then any 0, 1s equals true. If not any zeros, then sys out 0, else if not any 0, 1s, then sys out 1, else sys out 2. Okay, we get this first case wrong. They're saying the answer is 1? Oh, because you can do a prefix of zeros and then a suffix of 1s. Okay, so we want if it's all 0, 1s. Or should this just be the count? I guess we just need the number of 0 groups. Okay, so then let's figure out this logic a bit better. So if a at I equals 0, I guess we still want the same thing, right? So we want, if this is a 0 and the thing before us was a 1, then the number of 0 groups plus plus, because we have one more 0 group. And then if line at 0 equals 0, then n0 groups plus plus. So 1, 2, 1, 1, 2 looks right. I think we should be fine there. Looks good. Binary string that consists of characters. Awesome. Looks like we got it. And we're crashing, huh? I see. Okay. Guess we don't have any fun lights today, unfortunately. Okay. Max cut. What was this? Min-max cut? Kind of fun. Fun names. A binary string is a string. Okay, we know what that is. A bitable is a table that has exactly 2 rows of equal length, each being a binary string. Let max of a bitable be the smallest digit that does not occur in the bitable. Okay. Thank you. You're given a bitable with n columns. You should cut it into any number of bitables, each consisting of consecutive columns, such that the max of each column is exactly 1 bitable. It's possible to cut the bitable into a single bitable, the whole bitable. What is the maximal sum of maxes of all bitables? So here you cut this one, and then you cut this, I guess. So then you get 2 plus 2. Well, you wouldn't cut this, but you could go like this, sure. Yeah, so like, basically, at each step, you cut if the max is 2, or if the max is 1, and then following you is 1s. Yeah, okay. So we'll just like read in the input here. yeah, we'll just read in C. So C at I equals, okay, so if A at I equals B at I, then C at I equals A at I is equal to 0. If it is, then make us equal to 1. Otherwise, make us equal to 0. Else, C at I equals 2. All right, so now we have this C array, which is the only thing that's important. So int equals 0, 0 less than n plus plus. So if C at I is equal to 2, then ans plus equals 2, continue. If C at I is equal to 0, yeah, I guess Boolean free 0 equals false. Then free 0 equals true. We continue. If C at I is equal to 1, so if free 0, then free 0 equals false, ans plus equals 2, and continue. What if we don't have a free 0? So if I is less, or I plus 1 is less than n, and the next character, so C at I plus 1 is equal to 0. Then we process both of these at once, so ans plus equals 2, I plus plus continue. Otherwise, ans plus equals 1, because we'll just have this on its own. And then sys out the answer. 8, 8 to 12. Looks good. Kind of a greedy approach again, but we'll see how this does. Okay, D1 and D2. This is the easier version of the problem. In this version, n equals 1. This version ends up to 300. In the cinema, seats can be represented. Pretest pass. Nice. Seats can be represented as a table with n rows and m columns. The rows are numbered with integers from 1 to n. And the seats in each row are numbered with consecutive integers from left to right. In the kth row, so they're numbered like this. Row major order. There are n times m people who want to go to the cinema to watch a new film. They are numbered from 1 to n times m. You give exactly one seat to each person. It is known that in the cinema, the lower a seat index, the better you can see everything that's happening on the screen. Person A has a slight level of AI. The lower the seat index you have, the better you can see everything that is happening on the screen. So 1 is a better seat than n times m. You want to give better places to people with lower sight levels. Okay. After you will give seats to all people, they will start coming to their seats. In the order from 1 to n times m, each person shall enter the hall and sit in their seat. To get their place, the person will only go to their seats row and start moving from the first seat in this row to theirs from left to right. Oh, so they go like this and move over. Okay. The inconvenience of the person is equal to the number of occupied seats he or she must go through. Let's consider an example where m equals 5. Okay. Person has seat 4 in the first row. Okay, and seats 1, 3, and 5 are already occupied. Seats 2 and 4 are 3. The inconvenience will be 2 because you have to go through 1 and 3. Find the minimum total inconvenience. It is possible, giving places of all people with all conditions satisfied. All right, let's recap this because there's a lot going on here. We have some people and some rows of seats, right? Yeah, we've got some people and some seat rows. And we want the people who have lower site indexes to be farther up. Okay. So one seat to each person. All right, so we're given n times m integers, which is pretty small here. And we want to put the minimum total inconvenience. So, okay, so we have like, these are given in some order. So for these ones, we want to go left to right, okay. And then we have these, maybe all of these are given together. And then we have these are given together. Or maybe it's like these here. And then like these. So we have these 4 groups where each group is non-obvious. Obviously, within a row, we would want to do something like this. We'd want to do 1, 2, or we'd want to go backwards. We'd want to do 1, 2, 3, 4. Outside of a row, we would want to do something like this. We'd want to do like top to bottom. All right, we'd want to do 1, 2 to minimize the inconvenience of these ones here. And then 3, 4, 5, 6, probably. Yeah, so it seems like a pretty easy problem. Okay, apparently not trivial, or maybe trivial. Trivial if you're geothermal. So you split these up into groups. You have the size of each group in sorted order. Second test case. This one. Yeah. So we find if we sort this, we find like the size of each contiguous group. Then we have their orders. And then we, I guess, sort them. Yeah. So we can do this. Should we solve D1 first? I guess D1 is pretty easy. D1 is probably very easy. So we just, each person goes to, I guess we can just go from right to left and assign each person the rightmost spot. Yeah. And then change it to -1. Okay, so let's just do D1 to get it out of the way. So we'll sort this, and then into I and A, or into I, yeah, we want to go through each index in A and give it to the first place, probably. Yeah, we know where it has to go, so we'll just, or I guess the last place. 4 int 2 equals n minus 1, 2 is greater than or equal to 0, 2 minus minus. So if clone at 2 is equal to I, then clone at 2 equals minus 1. And then break. And then 4 int I equals 0 less than 2 I plus plus. If clone at 2 equals minus 1, then ns plus plus. So runtime here will be n squared per test case. Should be fine, I think. No, what? So the second one is not 10. 2, 5 through 3. Oh, clone at I. $3601. Okay, so we'll submit this here, and then onto D2. So D2 shouldn't be that bad, but yeah, let's do it, I guess. So we have int n and m. This will be n by m, and then we have int array a equals have s start read array n times m. Okay, and then we have int array sorted equals a dot clone equals sort. Then we want to assign each thing in the grid. Okay, so static class point. So a point will have an int x, y, and then a value. So these should all be things with the same value. So if y is not equal to o dot y, then we want the one with the smallest y first. Yeah, then return integer.compare y dot y. Otherwise, we want the one with the biggest x. Yep. So then for int x equals 0, so y all the way up to n, and then for int x equals 0, x less than m, x plus plus. Grid at xy equals sorted at index plus plus. Oh, this should be yx, because I'm doing this one backwards. Okay. And then, can we do n cubed here? 300 times, oh, 10 to the 5th. So we should be fine here. We can do this naively. Boolean array used equals new Boolean array n by m. x equals 0, which we print at the end. All right, so then we want hash map of integer to priority queue point map. All right, and then, so this grid is built. So then we want to, we'll do this in a minute. Let's build this first. For int y equals 0, y is less than n, y plus plus. For int x equals 0, x less than n, x plus plus. Point p gives a new point. This will be at x, y, and the value will be at grid at x, y, or at y, x. And then, if not map.contains key at grid at yx, then map.put grid at yx, the new priority queue at this position, and then we'll get whatever priority queue is there. And then add this point to it. Okay, so now we have this built. So then, once we do this, we'll go through the array. Go through each integer. And then point p will be map.getI.remove. And then used at p equals true. P.y followed by p.x. And then we want to update our count. So for int y, or int x equals 0, x less than p.x, x plus plus. If used at x and then p.y, or sorry, p.y and then x, then ans plus plus. So this should be fine. Null pointer exception. There shouldn't be. Why would this be the case? Sorted at index plus plus. X less than m. So 1, 1, 0, 4, 0. Looks right. Okay. How many test cases? 100, so we should be fine. Easy set so far. Submitted. All right, not bad. So now the contest starts. Buds rehanging. A tree is a connected graph without cycles. We know that. A rooted tree, we know what a rooted tree is. We know what a parent is. We know what a child is. Okay, a vertex is a leaf with no, wait, a vertex is a leaf. Okay, we know what a leaf is. Finally, new stuff. We call a vertex a bud if the following three conditions are satisfied. It's not the root. It has at least one child, and all of its children are leaves. Okay. And it's not the root. Okay, I see. You're given a rooted tree with n vertices. Vertex 1 is the root. In one operation, you can choose any bud with all its children and rehang them to another vertex in the tree. By doing this, you delete the edge connecting the bud and its parent, and add an edge between the bud and the chosen vertex of the tree. The chosen vertex cannot be the bud itself or any children. Okay, that makes sense. All children of the bud stay connected to the bud. What is the minimum number of leaves it is possible to get if you can make any number of the above mentioned operations? So you could, in theory, remove a leaf. You can make a leaf a non-leaf by attaching a bud to it. Yeah, so what is a leaf? Okay, if it has no children. So the root is probably never a leaf? Yeah, never a leaf. The root's never a leaf. And when we do this operation, we remove a leaf. Yeah, so this 4 can go to the 3. The 2 can go to something. So any leaf has either 1 or 0 buds attached to it. Is it just the number of leaves minus the number of buds? We have 2 buds, 1, 2, 3, 4 leaves. When is that not the case? So here we have 2 buds and 3 leaves. Oh, because you need... So sometimes you have a bud that's an ending bud. Wait. Yeah, so here you have like an extra one. So sometimes it's -1. So this is the number of buds -1. Because you can't move any of these things to something that isn't part of some bud. Here this is... We have 1 bud. Oh, but it creates a leaf. I see. Okay, let's think about this for a bit. This is an interesting problem, maybe. So if you have, okay, so let's say you've got something that's like this. So if you want, you can take this part, you can like get rid of this. So this can go over here. You've got this on its own. And then you have this on its own. Yeah, do you first just initially destroy the entire tree? Maybe just do that first. So first destroy the tree. Why would we not want to just kill the entire thing? See, I almost said why would we not want to kill everybody, but like, yeah, you gotta watch out. Sometimes these things will be taken out of context. Why would we not want to kill everybody? It seems like a good idea to kill at least as many people as possible. Like, other than the root, you want to keep, like, you have to keep the root alive. But you can imagine separating the root from everyone else. Because the root has distance at most 2, right? Because if it had a distance of 3, then you could chop this. So yeah, so like separate the entire thing. So just separate it. Okay, so let's say we've separated it, and now we have some things that look like this. No, everything is height 2. That's the constraint we have. We have a bunch of height 2 stuff. That's it. Okay. So we have a bunch of things that look like this. There is no, like, the way of doing this is unique. We can definitely do this uniquely. Take the deepest thing, remove it, yeah, then we're good. Oh, we just keep every edge that is in, like, an even height. Yeah. So we have, like, 2 subsets of trees. Or maybe. Yeah, every edge that's, like, even height will get cut. Okay, so, yeah, so we do that, we have this. And then one of these is the root. But every other one will subtract 1 from the answer. So -1, -1. So 1, 2, 3, 4, 5, 6, -2. Let's do this with samples real quick. So I think this would be a good case, probably. So we have, oh, interesting, we have just a node for the root. And then we have this. Then we have this. What if you have just a node for the root? What does that do? I guess you, does it count as a bud? Maybe, right? Let's say it does. Then minus, minus, plus, plus, plus. So the answer is 2. Yeah. Okay. So so what's interesting here is this is kind of, this is an interesting odd case. The number of, how many pluses are there? A node is a plus if it's the bottom of its component. So I think we can do this with just a DFS. We should be fine. Okay. So how do we do this? So we first start with n. We're going to need a node class. We'll have an array list node children with new array list. And then we'll say we've got a public void DFS, and then a Boolean cut above. Okay, and then what do we care about for this node? Well, we care about whether this is a root and so this is equal to cut above, and whether this is a leaf. When is something a leaf? This is equal to not cut above. So DFS, and then we probably also want the depth. I guess we don't need the depth. So we want the node parent here. I guess we don't need the index. So Boolean is root. Okay, so pair equals null, then is root equals true. Otherwise, children.remove the parent of this node. Okay, so this handles that. We want a DFS from all of our kids. Pass ourselves in as the parent. Then, if not an n.cut above, then we want to cut above us. Because we have an edge from him to us, so we cut above us. Okay. So now we've calculated this for all things. Okay, so then node array nodes equals new node array n. Make all these nodes, and then we want to say int I equals 1 less than I plus plus. So A will be this, B is this. So we have this edge. We want to say nodes at A dot adjacent or dot children dot add nodes at B. Okay. So we make this edge. Then finally we do the DFS. DFS from the root. Sounds good. Okay. So we've calculated everything now. And then we need to get the answer. So int ans would be 0. So for node nn in nodes. So if nn dot is root, then if it's the root, then it's the top of something. So then ans minus minus. If not nn dot cut above, then ans plus plus. And I think that's the answer. But we want to start with 1. Is that true? Yes. We want to start with 1 leaf. And then we print that. Two, 2, 1, 2, 1. Not even close. Okay. First case looks like this. Well, the next hypothesis, the answer is always 1 or 2. So we cut above, true, true, false. You cut above 0. So we cut above 2, above 4, and above 1. Oh, else, ans minus minus. So the answer is 1. Is that true? No, it's 2. This is the first test case. We get this. So we cut above 2, above 4, and above 1. Oh, I'm subtracting 1 here when I shouldn't be. else if not, and n dot is root. Yeah, so now the answer is 2. Okay. So 2, 2, 1, 2, 1. 2, 2, 1. Then the answer is not 6. Okay. So in this case, I'm saying the answer is 6, but it's much smaller. 1, 2, 3, 3, 4, 4, 5, and 3, 6. Okay, interesting. So we have 1, 2, 3, 4, 5, and then 6. So we cut this, and then cut this. Yeah, so we have I guess let's do this. Okay, we still print this. We don't cut above anything. Why would that be? Because I am an idiot, that's why. Tree is bidirected. It's really surprising I got the first case right, to be honest. 2, 2, 1, 2, 1. Looks good. Let's see how this looks when we submit. Nope, not B. E. This seems sketchy. There's some sketchy stuff going on with the root here. Okay, looks like we got it. Maybe now's when the real contest starts. Points movement. Oh my goodness. Sounds like a geometry problem. Nope, it's not. Darn. I got really excited there for a moment. We need more geometry problems in competitive programming. That's what I think. I feel like geometry problems are a little underused. And maybe the reason I say this is because I really like them. But also, I feel like a lot of people really don't. And I feel like that anger is misplaced. I feel like it's more just frustration that they don't have the tools required to solve them. And I feel like if people had the geometry tools, maybe we need some more algorithms thread on geometry problems. Maybe I should do that. Get back in the contribution ring. What do you guys think? I like the idea. I think that's a good idea. Once we have Facebook Hacker Cup chills down a bit, and after World Finals is over, sounds like a great idea. Okay. Back to the global round. Points movement. You got n points and m segments on the coordinate line. The initial coordinate of the ith point is ai. The endpoints of the jth segment are LJ and RJ. So the jth segment has 2 endpoints. Okay. You can move the points. In one move, you can move any point from its current coordinate x to the coordinate x minus 1, or the coordinate x plus 1. Okay. You want to move the points in such a way that each segment is visited by at least 1 point. Visited by what? Okay, so we have n points and m segments. We want to move the points such that every segment is visited by at least 1 point. A point visits the segment if there's a moment when its coordinate was on the segment. You want to find the minimum possible total cost of all moves such that all segments are visited. Okay, what is going on here? We have the first case. We have 4 and 11. 4 points and 11 segments. So 1, 2, 3, 4. Move the second point from coordinate 6 to coordinate 5. Okay. Move the third point from coordinate 14 to coordinate 13. Surely we need to move it to coordinate 12 as well. add to coordinate 12. Okay. So this third point will cover all of this. So yeah, so then we've covered all of this. And then the fourth point from coordinate 17 to from coordinate 18 to 16. Okay. Yeah, okay, that makes sense. So at least one annoying part of this problem is that you might move the same point both left and right. Like, hypothetically, it's very possible for something like this to happen. You can get, I mean, like, this can be a sub-mask of a harder problem, but you can have, like, this segment and this segment. And this point moves here, and then it moves back, and then it moves back again. And the fact this part is double counted makes it, like, annoying. No two points will ever cross each other unless they start at the same position, in which case they might move in different directions. Oh, they're all initially distinct. So they're all distinct forever. Drew's got this in 17 minutes. Dude, geothermal. Actually, so speedy. So speedy. This guy, hands of fire, I'm telling you. Literally, his fingers melt his keyboard. So quick. Wow. How much faster is he than me? Is he like, I guess it's not that crazy. I mean, it's still very impressive. And he's already submitting on it. Look at this. He's like 15 minutes ahead of me. That's still pretty quick. Considering it's like 30% faster. It's like 30% faster. Okay. That's quick. That's fast. Yeah. Alright, Cliff Bar time. I'm hungry. I've been up since 4:30. Since 4 actually. Guys, if I can get a Cliff Bar sponsorship, how amazing would that be? Yeah, we got this problem by the end of the contest for sure. Here's my idea. These blocks are mostly independent. Wait, no. Oh yeah, they are. So any segment that crosses 2 points is already satisfied, so we can delete it. So now the only segments that are of interest are the ones strictly between 2 points, and they're in like some block. And then we have to like satisfy this. So there are a couple of cases, like it's possible when we start, the left point, like it's possible that when we start this block, the left point is here. So it's like we need to know whether we have the left available. We need to know whether we have the right available. We need to know whether we have to return the left. And then we need to know whether we have to return the right. By which I mean, like, let's look at the right. So the right might initially be available for this, which means we're gonna, like, let's pick a better color. So we're gonna move the right point over to satisfy some things. So let's say we move it over to here. This will satisfy everything. We might be able to leave it here, but we might have to move it back to go satisfy things in here, right? Because this one might be moving out this way. Or like, yeah, this one might be really far away and can't handle it. So we might have to move this left and then move it back right. But we'll imagine splitting this up along this line here. Yeah, this will be a really pretty screenshot for a thumbnail. Look at that. Boom, beautiful. Okay. I think that's the idea. And then we can do like some, so this is like one thing. We need to calculate each of these things. And then we can do like some DP probably, where we're like DP at some index. This field, I don't have the details fully worked out, but I'm pretty sure this leads, this idea, like the end of the solution path doesn't wind up being, oh, this is actually impossible. Like this winds up being like, okay, and you can get it correct from here. So I'm just like, I've done this before. This is the kind of intuition you have that this will end up working. So you're at some index and you know that, or you want to know, yeah, at some point. Oh, maybe we should do it at, yeah, so let's do it at a range. This is which range you're at. And then whether you have the last, have left, I guess. And then there are two options. So if you don't have left, then this is like right only, and then return right. And then you can do right only and then leave right, like leave it in the middle. And then otherwise, yeah, you have the other cases. Okay, so this is, yes, this works. Where did my notes go? Okay, so here's the solution. Now we just have to implement this, which will take probably about half an hour. Okay, the real question is, can we get it right on the first shot? So we have the number of points and the number of segments. Okay, so and distinct integers, which are the coordinates of the points, which are not necessarily sorted. Do we want these to be in a tree set? I don't know. Compare L to O dot L, I guess. New seg array. N segs. So we'll have these points. Where do the points range to? Negative this to this. Yeah, so I guess we'll just make all of these longs. Okay, so this would be endpoints plus 2. Endpoints plus equals 2. And then, okay, so let's say points at endpoints plus plus equals long 1e12. And this will be negative 1e12. And then make this a long array. So we do this with the points. Now we have to read in the segs. Okay. So for each segment, we read the L and the R. So this equals new segment from this to this. And then, I guess we don't need to sort the segments. Shouldn't matter. Now we just need to find the first, yeah, I guess the index. Okay, so public int get index of, so this will be int x, and then like returns -1 if equal to some element. And then long array, I guess this would be a long x, long array a. Yeah. Okay, so then for each segment, we need to add it to which gap it is. So we'll have an array list of segment array gaps. There's a new array list of segments. Oh, a new array list array of size endpoints -1. So we need to first figure out for each of these which one it's in. So for seg s in segs. So if, yeah, so we need the gap. So g1 equals s, or get gap of s dot l with these points. And then g2 equals get gap of s dot r with these points. So if g1 and g2 are different, then continue, or g1 is equal to -1, then that's also illegal. Otherwise, gaps at g1 dot add this segment. Okay, so how do we get this gap? We need to say int l equals 0, r equals a dot length -1. So well, l is not equal to r. Yeah, so this is gets the last index less than or equal to x. Okay, so if a at L is equal to x, then return -1. Otherwise, return L. So how do we do this binary search? So int mid equals L plus R over 2. If a at L is less than or equal to x, then L equals mid, else R equals mid -1. Yeah, so this should get which gap we're interested in. Okay. All right, so we have each of these things. So now we just need to solve this. Okay, so we need static int array solution for gap. Int array and gaps, I guess, and gaps equals endpoints -1. And then arrays.fill this with -1. Okay, so I don't know why we can just I don't need to fill this. Okay, so we need some method here. So static int solve. So what will this take? So Boolean have left, Boolean have right, Boolean return left, Boolean return right, int left index, int right index, and then we have this array list of segment segs that we have to satisfy. So that won't be too hard. What do we have to do here? So solution for gap at ijg equals solve for I equals 0. Oh wait, we need 4 booleans here. Ah, so much stuff. Okay, 2x2. I guess let's just make this 2 to the 4 bit mask here, because this is not that bad, right? Yeah, we're fine. Okay. Cool. Then make this, clean this up a bit. Less than 2 to the 4. So let's rename this mask. We also need the, yeah, okay, and then okay, so these aren't actually booleans, they're actually base 3 numbers, but that's fine. have left, have right, return left, and then return right, and then return left, and equals have left, return right, and equals have right, and then return solve, have left, have right, return left, return right, left, right, segs. Cool. Yeah, and then we need to use this thing at the end, but we'll do that in a minute. Okay. So I guess static int get ints. Well, yeah, we'll do that in a minute. Okay. Fine. So solve for gap at, this is the mask, this is G. We'll solve, or equals, I guess, just call solve. So the mask is this, the left is points at G, the right is points at G plus 1, and then we have gaps at G. What is wrong with this? Oh, these are longs, okay. All right, okay, so next part is this solve method. How do we do this? So we have some stuff. We have some restrictions. And we have some split point. Yeah, so let's say we knew what the split point was. Then we care about the left endpoint to the left of it and the first right endpoint to the right of it. I guess we'll do left one will go toward it if we're concerned with that, right one will go to the right of it. Are all the coordinates small? No. Darn. Okay. Yeah. So we'll get all interesting coordinates. Do we have a nice time limit on this at least? 2 seconds. Could you not have given us like 4? Okay, so we'll get all interesting. Yeah, so this is going to be 2 to the 4, which is 16 times log times n. We might need to speed this up and do 3 to the 4 instead. Or 3 to the 2, which is 9. Yeah. I guess we'll speed this up. We'll do that later. So, yeah, we want to get all interesting cut points. And then we want to consider first L left of this, and then first R, like less than or equal to, really. First L less than or equal to, hello? Less than or equal to this, and then first R greater than this. Okay. All right. Yeah, so we can do this. Okay, so if segs dot is empty, then return 0. If not have left and not have right, then return 0, or return, I guess this is going to be a long. Return long dot what's infinity? Return infinity. Okay, so if not have right. Okay, so otherwise we want a tree set of all lefts and all rights. We can probably also we might also always have the right. So okay. So this is all lefts equals new tree set. And then all rights equals new tree set. Hello. So for each segment, we'll say all lefts dot add this segment's left endpoint, and then all rights dot add this segment's right endpoint. So then, yeah, oh, these are longs actually, not integers. Then we want to say, oh, this is returns a long now. Okay, and the solution is a bunch of longs. Okay, so then, hello, give me my editor back. What's wrong with this? New long array. Okay. And this is not plural. Okay, so we get all of these. Okay, so now if not have left, our answer will be all lefts dot last minus left index. And then return, if we have to return left, ans times 2, otherwise just the answer. If not have right, then long ans will be all rights dot last, or dot first. And then it'll be the right index minus this. And then return, if we have to return the right, then ans times 2, otherwise just the answer. Okay, so cool, we should be good there. Ans times 2. So this handles the case where we don't have both of them. Now we do have both of them. So now we need to brute force the middle point. Okay, so we need a hash set integer interesting equals new hash set. We don't really need this. Yeah, let's just make an array list of long interesting equals new array list. So for seg s in segs, interesting dot add s dot l, interesting dot add s dot r, and then add s dot l minus 1, and then s dot r minus 1. We could do a hash set here, but I think the hash set overhead, like worst case, these are all different anyway, I think. So it shouldn't matter. Yeah. I think this should be fine. So then for int split, I guess long ans equals 0. Ans equals infinity, I mean. So int split in interesting. So long L equals all lefts dot floor of split, and then R equals all rights dot ceiling, or dot higher of split. and then long cost equals 0. So if L equals null, or if L is not equal to null, cost plus equals, if we have to return, okay, long L disk will be L minus left index, and then cost plus equals, if we have to return return left, then L disk times 2, otherwise just L disk. Alright, and then if R is not equal to null, how much time do I have another 7 minutes left for this, we should be fine. So then long R disk will be R minus right, or will be right index minus R, cost plus equals return right, if so, R disk times 2, otherwise just R disk. And then ants equals math.min of ants and cost. Okay. Yeah, cool. So we're good there, we're good there, we're good here. This should be fine. So yeah, okay. So we can speed this up now. So if return left and not have left, then return infinity. If return right and not have right, then return infinity. Okay. Otherwise we return this. Okay, this gets passed in here. Good, good, good. And then all we have left is a DP. Static long go. So this will be int gap, and then int have left still. Okay. So then static long array dp. Okay. dp equals new long array 2 by n gaps. Okay, and then what do we do here? So if gap is greater than n gaps, then return 0. So we need, I guess, and that return 0. Otherwise, okay. Oops. Okay, so if dp at have left still and gap is not equal to -1, return this. Okay, so if we still have our left, then we want to use it. So Boolean have left, Boolean have right, Boolean return left, Boolean return right. Long left. Oh yes, and then just int gap. So int mask will be have or equals 0. If have left, then mask plus equals 1 left shift 0. Okay, and then just return, what is this? What did I call this thing? Solution for gap at mask gap. Okay, good. So we have this. All right, so now we can call this pretty easily. So have right will always be true. Okay, so if we have the left still, then we can use left for free. So long, okay, so we can either, this will be use the right without returning it. I guess we want to keep the right. So this is ants equals math.min of ants and some stuff. So go gap plus 1, have left still will be false, plus get answer. Do we have the left? Yes. Do we have the right? Yes. Do we return the left? No. Do we return the right? No. And then this is the gap. Okay. And also return the right. So we do have the future left. We do have the right. We don't need to return the left. And then we do need to return the right. Okay. Otherwise, we do some other stuff. So this is if we don't use left. Okay, otherwise we need to do use left. Okay, so we're not going to use the left segment, which means have left is false. Do we have the right? Possibly. Yeah, so okay, we do have the right always. Do we return the left? Well, I guess it doesn't matter. Do we return the right? False. And then we don't have it in the future, or we do return it, we do have it in the future. Okay, otherwise we do use the left. This is two more things. I guess none of these, we don't need any of this nonsense. It just makes the code long and hard to read. So we'll just do this, because maybe this is a useful gap. Very much overusing the word gap today. This is fine. Okay, so in this case, we're going to do something similar. What do we do here? So we do use the left. So we have this for both of these, and in both cases we need to return it. Yeah, and that should be fine. And this is whether or not we have it in the future. Okay, good. Yeah, and this should be good. Okay, so I think this is the answer. So then finally, gap 0, still have left? Yeah. What are the odds this is right? How cool would that be? Took almost exactly half an hour to implement, right? Okay, no, never mind. It took longer, but crash. Gaps. Array index out of bounds 5. What? So here are the 4 things. 1, 2, I guess let's just put it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4, and then 12. Okay, so here's the first case. Do I sort these? Negative big number. These are all zeros. What? Oh, because I never read them in. Yeah, that would do it. So we have to actually read them in. But this still should be fine. Okay, anyway. Okay, so the points is 2, 6, 14, 18. 2, 6, 14, 18. Okay, that part's fine. That's pretty easy, to be fair. And then, what are we doing here? This is a different crash, okay. Or maybe it's not? Yeah. Great, index out of bounds exception at 5. It's got to be the gap. If gap equals minus 18. It's a pretty impressive answer, I gotta say. How is it minus? Okay, so so some of these are minus. Yeah, let's look at this. So the first negative one is solution for gap 1, 0. So this is 0, 1. So it'll be so we do have right. So we have right. Why is that? S.L is less than left index. Oh, I guess, yeah, so this interesting one could be, well, it shouldn't be. Yeah, it should be fine. Okay. Good, so let's do a two-string here. Out, adding S to gap plus G1. All right, so adding 0 to 3 to gap 3. That sounds not right. 0, 1, 2, 3. Okay, that's not right. So points are these things. 0 to 3. If this isn't equal, okay, so get gap of is wrong. I can't write a binary search for my life. L plus R over 2. Yeah, okay. If AL is less than or equal to mid, then L equals mid. Otherwise, R equals mid minus 1. What? Okay, gap of 0 is returning 3. Okay, gap of 0. Yeah, it's not 3. Can I really not just write a binary search? Okay. So 0, 5. Ah. Is the answer 5? It is 5, interestingly. Okay. 17. The answer is 22. Oh no. That's disappointing. Okay. All right. What do we do here? We have a break case. That's nice of them. Okay, so let's see. So if this is sanity check, please be negative. Darn. Okay. Okay, yeah, let's draw this out on paper. Give us a draw. That would be really nice of them if they did, wouldn't it? So here we go. So it looks like this. just this case. What if I get just this one right? How cool would that be? Be awesome. We're not there though. Oh, they can be negative? Does that matter? Does it matter? Does anything use the sign or do any division? Probably not. But we could just do this and check. Okay. Now if this isn't 17, okay, it is 17. So yeah, it shouldn't matter. My hypothesis is it doesn't matter. Okay, let's actually figure this out the right way. So stuff goes from like negative 20 to 20. So we'll just do this in centimeters. 20, 15, 10, 5, 0, and then we'll add so we have each of these. Oh man, it goes to negative 20. Try again. I guess with this by 2s then. So minus 20, minus 10, 0, 10, 20. So our special points are at minus 16, minus 9, (3) and 12. Okay, lines are minus 20 to minus 18. Minus 14 to minus 13. 18, 16, 14, 13. Okay. Minus 10 to minus 7. Minus 3 to minus 1. Zero to 4. 6 to 11. Seven to 9, 2, 4, 6, 7 to 9, 8 to 10, 13 to 15, 11, 12, 13, 14, 15. 14 to 18, 16 to 17. And then 18 to 19. Okay. So, yeah, so in this case, 2, 3, 4, 5, 6. So this is in fact 6. So dp at 4, 0 equals dp, or equals 6. dp at 4, 1 should equal 6. Hopefully I haven't misread the problem. Now it's ready to figure that out. Okay, interesting that these are basically always the same. Wait. It's have left, have right, right? Oh, because we always do have the right? Yeah, you can just not use the right. It's the same as not returning it. Yeah, okay, that's fine. Okay, what about dp at 3? So dp at 3, 0. Saying we can get everything in 3? 1, 2, 3. I don't think you can. Oh wait, should this be dot ceiling? No, it should be dot floor. Yeah. So this one. So we do use the left and we keep the right. Wait a minute. 4, 0. What? Well, this should not be 6. This should be a very large number. So have left still is false. So, okay, so this is not right. So print at gap equals 4, have left still equals 0. Yeah. So this first one is 6. So we don't use the left. Have left is false. Have right is true. Oh wait, we don't have right, we don't have left. Okay, 22 is the answer. Good, nice, thank you for the test data. Test cases, 10 to the 4, should probably be fine. I'm a little worried about time, but we'll see. Wrong answer, test 2. TLE test 2. Oh no. Oh no, am I gonna TLE? Oh no. Oh no. Okay. So what part of this is going to be slow? Darn it. Okay. I am memoizing, right? Yeah. Answer should always be positive, I think. We shouldn't need any of these anymore. Okay, so get answer. This is order 1. Yeah, this part should in theory be fast because we do some stuff. Okay, so can we not minimize this? Eclipse, what are you doing with your life? Let me minimize. Okay. All right, so this is fine. But we always yeah, we always have right. So we don't need have right. We don't need this. This can be 1 and then 2. Then we don't need have right, so this can be 1 and then 2. Have right is always true, so don't need to worry about that. Don't need to worry about this. Have right is true. This is never the case. This is never the case because we always have our right. We can get rid of the tree sets. Yeah, we don't need the tree sets. can speed up a factor of 8 if that's really killing us, but it's almost certainly the tree sets. Okay, so these all rights at 0. Okay, so we need floor and higher. So static long floor, long x, long right A, and then static long higher, long x, long right A. Less than a at 0, then return long dot max value. If x is greater than or equal to a at a dot length minus 1, return long dot max value. Okay, so yeah, so now int L equals 0, R equals a dot length minus 1, well, L is not equal to R, do some stuff, return L. Int mid equals L plus R for 2. If a at mid is less than or equal to x, then L equals mid, else R equals mid minus 1. L equals 0, R equals a dot length minus 1, well, L is not equal to R. Int mid equals L plus R over 2. If a at mid is greater than x, then this is good, so then R equals mid. Otherwise, L equals mid plus 1. Return L. This should be somewhat faster. Darn it. Okay. I'll return A at L. $25. So floor int sorting these? We are. Okay. Oh, so it might not be this actually? So, yeah, let's try just removing the tree sets here. Tree sets in the solve method. Yeah. Sorry about that. Yeah, so we're fine there. I guess let's just make sure this isn't. Yeah, okay. And then int all lefts index equals 0. All rights index equals 0. Man, why is this problem taking me so long? Ugh. Okay, all lefts at all lefts index plus plus equals s dot l. All rights at all rights index equals s dot r. All lefts at all lefts dot length minus 1. Oh, this is if x is greater than x. Okay. I wonder if that were the problem. Okay. What if is this? No, okay, something else. So now equal to long dot max value. Okay, so we're good here. We're still correct. I broke it in doing this change. So the difference between F2 and F3 is this. Okay, what would change? So my floor and seal. Oh am I not calling floor? I'm not sorting, am I? Solve. Okay. So slow. Really? Why so slow? Okay, maybe it's the sort. Sort long negatives. Guess we'll do print writer, so we might as well. What is the problem here? Wait, so what are we guaranteed for this? Am I missing an important guarantee? The sum of n and m are both small. Oh, this is now n squared. Okay. So that actually should have TLE'd. But if we do this, then it should be correct. So that should be correct. Next optimization is get rid of some of this state. It's a little bit faster. Still TLE. All right, we can speed it up a bit. I think. Oh well. What do we need? Okay, so we can. 17 minutes to get this, huh? This is kind of silly. So have right, we don't need. So there's that, and this should be 1 and 2, and then this should be 1 to the 3, 1 to the 3, and then have right should not be a thing. Ants, we don't right. Okay. Is still correct. Looks like it. All right, and then we should not need to pass all of these in and sort them. Okay, call solve. So static long array all lefts. So for int g equals 0, g is less than n gaps, g plus plus. Okay, I do have one more trick up my sleeves. So yeah. We can do divide by 2 speedups. Make those bit shifts. Okay, so we don't need this. This is, all right, so we need this array list seg segs equals segs and g. Okay, I guess there's segs and g. Oh, it's just gaps. Null pointer exception. Okay, divided by 2, this is shift 1, right shift 1, right shift 1, Are you kidding me? ideally earlier? Dude, why? What the heck? Okay, what if you make all the longs ints? That, we don't need this. Oh, I guess. Let's just look at this submission. Might help. All right, otherwise we can speed up this a little bit. We have a bunch of query points and a bunch of answer points, so this can go faster. Oh, I'll just one. What part is slow? Why is this slow? Dude, what? Let me pass. This is obnoxious. This would totally pass in C++. What the heck? What the heck? Dude. It's gonna get hacked. It's gonna get hacked. It's gonna get hacked. It'll get hacked. It's gonna get hacked. Okay. Alright, we gotta shuffle this. We're gonna get hacked. Okay, so if length is small, that'll probably be fine. What if the length is big? Foreign I equals 0, less than a.length, that is plus. So random dot next. Temp will be a at I. How long? Let's just try this. What the heck? What am I doing with my life? Okay. Int O equals random next int a.length. Oh, no, erase that, sorry. Okay, this will actually pass. Oh, that's dumb. My rating sort's slow. Well, you learn something new every day, I guess. Wow. Yikes. This was rough. That was rough, dude. That was rough. Ugh. Hit a wall there. Man, this was not even, like, I know how to do this problem in like 5 minutes, or I don't know, some number of minutes, not that long, and then it just took forever to implement. I spent half an hour speeding it up after it was right. Like, the base idea, nothing changed. I just like got rid of tree sets, I did some other wacky optimizations, and then I had a bad sort, I guess. Ugh. And this is probably breakable? Question mark? Possibly. It's possible this is hackable. This one shouldn't be. This should be unbreakable. Well, actually, that's not true. Or do I seed my random? I do. So it's hackable, but like, no one's gonna do it. It's very unlikely that it's hacked. They would have to be in my room, and they would have to predict my random seed. So if it is hacked, I'll just submit it when it's hacked at the end of contest. But yeah, so that's right. Oof. Yikes. Okay. Did, who got the Rainboy? The legend. Look at this. Dark green on H. He solves the problem, Tourist doesn't. Is Tourist in first still? Look at this, is amazing. Look at this. Rainboy Rainboy, dark green's H, solves a problem that tourist doesn't, and gets like last place. Oh man, oh my goodness. Oh my goodness. Look at this. This is hilarious. This is actually so funny. Unless he fails system tests, but still, that is glorious. Okay. Yeah, what about G? I feel like this isn't that bad of a problem. I don't know. I haven't read it. Wish I had time to solve it. Ugh. Yeah, I don't know. I feel like this was a fun contest, and I didn't do that badly, but I don't know. Okay, what do I need back to get IGM? A decent amount. I need 70, so I'm not going to get it unless there's some system test movements. Because of my wrong answers, I guess. Perfect setup until F. And then I solved, mentally, I had it pretty quick too. It just took me forever to implement. Unfortunate. Okay, well that's the contest. Let's talk about solutions, I guess, here. Okay. Yeah, I guess let's look at standings real quick. So, yeah, I didn't get hacked, which means this will, in all likelihood, pass system tests. Yeah. How's this guy doing? Yeah, so, alright. How are my friends? Wisconsin, good to see ya. Greatest state in the union, I tell ya, although you're from Ukraine, so not quite. Rainboy, you know, just so many applause here. Well done, sir. Well done. Okay. Solution time for real. Enough looking at the scoreboard. That was fun. Yeah, let's talk about problems. So, not too bad today, but we can talk about them. Median minimization, maximization. So in this problem, you have some fixed length of an array. So maybe you want an array that's like 5 elements long, in which case the median, if it's sorted, is going to be this element, and you want the sum to be equal to some value. Now, I'm going to change the problem a little bit and say we want the sum to be some value or less. And we'll see why that's a legit change in just a moment here. And we want the median to be as big as possible. So let's say the sum is equal to 10, or let's say 9, for instance. And we want the sum to be at most, or let's say the sum is equal to 9, but the problem says we need a sum equal to 10. Well, we can just keep increasing this last element until the sum equals 10. So if a solution is valid for a sum equal to 9, we can make a solution valid for n equals 10. That doesn't make our answer worse. It'll make our answer better or the same, but never worse. So we're gonna read the problem. Instead of the sum has to be equal to n, or equal to s, we'll say the sum is less than or equal to s. Okay, once we have that, what the problem is we're given some array, and we want the sum to be less than or equal to s. And all we care about is the median, right? And we care about all of the numbers after the median. They have to be at least as big as the median. So we'll greedily make everything as small as possible. These things in the beginning, they have to be at least 0, so we'll make all of them 0. And then each of these things, we'll make them all just be the same value, because they have to be sorted, but we'll make them each the same value. So let's say we make all of them like x. Now, the question is, we have 3 of these, right? So it's 3 times x is going to be our total for whatever x is. And we want this to be less than or equal to n. So if we do some math here, what that means is that we know x is equal to n over 3 floored. Yeah, so we just have to figure out how many x's are there going to be. And it turns out the answer is just n plus 2 over 2 floored. So in this case, n equals 5. So 5 plus 2 over 2 is 7 divided by 2, which is equal to 3. If n is even, let's say n is equal to 6. In this case, they decided the median was the first of the elements. So you've got these 6 elements. The median, if these are sorted, the median's this one, which means 6 plus 2 over 2 is 8 over 2, which is 4. So it works that way as well. So the solution is just s over n plus 2 over 2 floored. And this is also floored. Yeah, so that's the solution, which is super clean to implement. Just looks like this. Boom. Okay, cool. So that's problem A. Problem B, min-max cut. So yeah, this teaches you about max again. There was max in, not the last round, but the round 2 rounds ago. And this is like an interesting thing to know. It's just the smallest number that doesn't occur. So in this problem, you're trying to minimize the max, where you're going to cut an array up, and you want to minimize the max of all of the numbers, or the max of each of the sequences. So the first observation is that the smallest max possible. The smallest max possible is definitely 2 or less. You can always get a max of 2 because the max of the entire array is going to be 2. So you can get a max of 2. Man, you can get a max of 2. The question is, can you get a max of 0 and can you get a max of 1? Well, if the sum of the maxes of each of the sections is 0, that means we definitely need to have no section have a max of greater than 0. Which means the only way that's possible is if the entire array has no zeros in it, if it's all 1s. Because if there's any 0 in the array, whatever section includes that will have a max of at least 1. Possibly 2, but at least 1. So yeah, that's the first case. It's possible the array is all 0s, or is all 1s. And if this is the case, the answer is 0. If the array isn't all 1s, then we might be able to get an answer equal to 1. And this is the case if the array contains only one group of 0s. So if it's got a continuous range of 0s and then possibly 1s on either side. If this is the case, we can split the array up like this. So we can split it up into 3 groups like this. And then this will have a max of 1, and these 2 will both be 0. But if we ever have 2 0s separated by a 1, then the answer is impossible. So this will be the answer of 1, where any of these sections can be empty. Otherwise, the answer is 2. So yeah, that's the solution. The way I implemented it was slightly suboptimal. You can do this all with regex and make it really clean, but I just used for loops. So if there are any 0s, then you have to store that. Otherwise, I counted the number of continuous 0 groups just with this for loop here. So if it starts with a 0, that's one group. Otherwise, I count the first 0 in each group. So if you have a 0 where before it you had a 1, that's a new 0 group. So if you have no 0s, then the answer is 0. You can just pick the entire array, that's 0. Otherwise, you take each of the 0 groups as one of your groups, and then your answer is 1 if you have only one 0 group. Otherwise, the answer is 2. Okay, that's the solution to B. C is not too bad. Here's the idea for it. We have 2 arrays basically, and then we're going to cut them in the same positions. Man, 0 is freaking out over here. We're going to cut them out in like the same positions, and then what we're going to do is we want to maximize the sum of max of each positions. So before we had an array, but now we have like 2 arrays. So maybe the arrays look like this and then this. What we can do here is we can cut things here, here, and here. And then our sum will be the max of this grid is 2. The max of this grid is 2 because we have both a 1 and a 0. And the max of this grid is also 2, so the answer is 6. So yeah, just a greedy approach works for this. You can just like make a couple observations. So if a section has both of these, we'll make it its own section. Right? There's no reason, if it has a 0 and a 1, there's no reason for us to include anything else. So we'll just leave it alone. If we have a 0, let's say we're going from left to right. If we have a 0, if there are 1s after this, like obviously if there's a 0 and a 1 after this, then this is going to be its own thing, right? So we might as well just make ourselves our own thing if that's the case. But if the thing after us is just 2 1s, then this thing will be useless unless it's combined with a 0. So we might as well combine these two together, and then we've gotten the maximum possible benefit out of this rightmost set of 1s. So this is like one optimal way of doing it. If we have a 0 and then right next to it we have the 1s, you take those. And the only other case that's left is if we have some 1s here, which haven't been matched with a set of 0s to the left, and then to the right of it, we have a set of 0s, then we'll match things like this. And then we'll take this root. And I guess those are the 3 cases. So I guess the last case is if you have neither of these, then you might just have a pair of 0s alone, right? And this will give you 1 point. The rest of these will give you 2 points. So yeah, you just do these in a greedy order, and that'll give you the best answer. You can prove why this is best, but it should be, I think it's pretty intuitive, I think. Why is my camera gone? Good morning. Dude, okay. Well, I suppose the failure condition is now slightly better. Now we have a new camera. It's very tiny. I guess we can do this without the camera. Yeah, I suppose so. Okay. Yes, that's the solution to that. Man, sorry with these camera issues. Dude, I also just got a new camera, or a new adapter to possibly solve this issue, but apparently that's not it. So I don't know. Okay. Yeah, so that's C. Let's move on to D. Yeah, so for problem D, we've got this series of seats in a movie theater, and we want to assign the people in a certain order in row major order. So the people with worse eyesight have to be closer to the front. In addition to that, we want to make it so that the people have the fewest total inconvenience among all possible ways of doing that. So importantly, there might be a tie, right? There might be 2 people with the same bad eyesight who both need to be somewhere in the front or whatever, but since they have the same bad eyesight, you have a choice of where to put them. So when you make that choice, you want to do it in such a way that the total inconvenience is minimized, and the total inconvenience is the number of people they'll pass if they go from left to right. So we can do some example here. Let's say we have just 2 rows of people. And let's say the people that will end up in all of these seats have the same eyesight. They each have like an eyesight of 2. The people in these seats have an eyesight of 1. And the person in this seat has an eyesight of 3. So one thing to notice is you are going to have continuous groups like this, right? So each group will be a continuous section. And then it'll be a suffix of something, maybe some full rows, and then a prefix of the final row. So now, when we have these people, we'll have some order. So maybe the order is like 1, 3, 2, 2, 1, 2, for instance. And the question is, when the people are gonna enter the theater from this order. The question is, when somebody enters the theater, so like when we have this guy enter the theater, for instance, which 2 seat does he go to? So we have to reserve these 3 seats all for people of length 2, but which one is this first guy going to go to? You get to make that choice. And the answer is we can sort these in some way that will minimize the number of conflicts we have. And it turns out that's pretty easy to do. So the first observation is for a bunch of 2's in some continuous row, we want to sort them like this, right? You want to go as far into the row as possible, because that way, you know, any of these places, like any 3 will have to walk past you, and anything before you won't have to walk past you. So the only thing that matters is the other 2's in your row. Those are the only people you'll affect. Each of those people, you might as well just like not bother any of them, right? You can always go to the end, so that's always at least as good of a strategy. So just do that. And that's like the greedy observation there. So yeah, so for some row, if 2 things are in the same row, go to the farther right one. The last observation is that you might have a choice between 2 different rows. And if that's the case, this is only a problem for D2, but if that's the case, we can figure out which one's better by just taking always the top row. And the reason for this is that all of the other rows, the only people who depend on you will be other 2's. But for the top row, there might be people who are a different number who depend on you. So for all of the rows that are only 2's, you know no 2 will conflict with another 2, because we'll always place them right to left. But for the top row, that's not necessarily the case. For the top row, we might have 1's that we have to place before this 2. So we want to get this 2 out of the way as early as possible, which is why we always want to place things from top to bottom if they're in 2 different rows. Yeah, and then that's the idea behind that solution. So we read in the grid, we like figure out what each position in the grid, like who's going to end up there, and we just like sort it and then put stuff in row major order. And then for each number, we have a list of all of the spaces that number can go to. So that's what this is. Like this is the person's eyesight, and for each eyesight, we have a list of the places they can go to. And then we say for every, we go through each of these XY grid, we build up, okay, what are all the places that someone with this eyesight can go to? We just add it to that hash map. And then finally, we just go through the array, and then we put this person in the next space they can be at. So the only logic I haven't talked about yet is this compare to function. If these 2 things have different rows, then the person with the higher row should go first. Otherwise, the person with the rightmost x should go first. Notice these 2 are backwards. So that's why the rightmost x happens before the leftmost x. Yeah, so that's the solution to D2. This will also work for D1. You can simplify it a little bit if you're only trying to solve D1, which is what I did in contest, but I think for explaining it, that part's not too important. Okay, last thing, or 2 more problems. So for problem E, we have some tree that we're given. It's a rooted tree. And we can do this operation of picking one of the nodes of the tree so that this node has a current height of 1. So we can pick node 2 or node 4 in this case. And then we can remove this node from its parent and then give it any new parent that we want. So in this case, we could take this, remove it from its parent, and give it parent 7. Let's draw what that would look like. So we have a tree that looks like this. We can erase this edge here, and then we can take this and move it over to this, for instance. This is one possible operation. So then this is what the new tree looks like. We can do it again. We can only do it to the same node here, but yeah, you kind of get the idea. Okay, actually this isn't the initial tree. The initial tree looks like this. So yeah, like another operation you can do is you could take this here and you can move it to this part. So you could do something like this. Like this. And then you could take this part here and then you could move this down. This. And if we do this series of operations, then our tree has exactly 2 leaves. We don't count the root as a leaf. So we want to minimize the number of leaves the root has, or the tree has, by doing a series of these operations. And each operation is pick some node that has only children, and you can give that node a different parent. So, okay, a couple observations here. The first is we can just destroy the entire tree initially. So we're going to do that. Let's look at what the tree looked like before I did all these operations. So what we can do here is we can actually just like make all of the cuts initially and then paste everything back together. So here we would cut this edge, and we would cut this edge. And I'll draw the cut edges in blue. But the important part is, like, we can do a pretty simple DFS to figure out which edges get cut. Specifically, we will keep an edge to a parent if none of our kids are attached to us. So this node has kids attached to us, or it has, we'll cut this edge if we have any kids attached to us. So yeah, so this edge gets cut because it has kids attached to us. This kid gets attached to its parent, so yeah, you leave it. This also has an edge to its parent, so you cut this edge, but this edge here doesn't get cut because this doesn't have any edges to its parent that are red. So, okay, so we have all of these. So now we can do a DFS and get which edges get cut and which edges remain. So we have these 3 components like this. Now one of these is the root, but it doesn't really matter. And here's why. Every time we have one of these top edges, this will subtract 1 from the number of components we have. And every time we have a bottom edge, this will add 1 to the number of components we have. So the answer is just the number of subtractions minus the number of additions, plus 1, obviously. Because one of these negatives has to be the starting point. Right? So the one that's the root, we don't actually get to subtract 1 from. So it's like this. And then we can just pair things up like this. You can pick any negative, combine it to any other positive, like this, and we're good. There's one special case here. It's possible the root itself doesn't have any children. So in this case, the root is both like a minus and a plus. And that's the only special case to watch out for. Because here we do something like this. So yeah, hopefully that makes sense. The code for it is not too bad. So we're going to do this DFS. We store for each node whether it's the root, and then whether we cut above it. And then we do the DFS, and then we iterate through each node. If it's the root, then it has a minus. And if we cut above it, or if we don't cut above it, that means it's a plus, because that means we're a leaf. So everything will be height 2. We'll have a bunch of components of height 2. Each one will either cut above, so each node is either the root of it or it's one of the leaves of it. And yeah, so if it's a leaf, it's a plus. Otherwise, it's a minus. Now the root, we've already counted the minus for it, so we have this. Yeah. So root is either just a minus or it's a minus and a plus. Or sorry, yeah, that's correct. It's either just a minus or it's a minus and a plus. Okay, cool. That is problem E. All right, last one is problem F. Points movement. Yeah, so in this problem, this is pretty simple to explain actually. We have a bunch of segments, or we've got like a number line. We have several points that we're given. So maybe we were given like these points here. And then we're also given several segments. So maybe the segments look like this. Yeah. Okay, so we're given some points and some segments. On an operation, we can take one of these red points and then we can move it either one space to the left or one space to the right. And what we want to do is move the points a bunch so that we will have had a point on one of the ranges of each segment for every segment at least once during the period of time we were doing this. So we can like take this red point, move it over like this, keep moving it over, move it over to here. So now it'll be here, it'll intersect this segment. Then we can move it all the way back to here. and then we might take this point and move it all the way over to here. And you move it just by plus or minus 1 each time, so this isn't just one move, this is like several moves, so this would cost several operations here. And the question is, what's the fewest number of steps it takes to do this? So yeah, a couple observations. The first one is that these points are initially sorted, right? Or we can sort them so that they are initially sorted. Once they're sorted, we always keep them in sorted order. So there's no way for one point to want to travel across another, right? Once 2 points are next to each other, they're fine. The second observation, which I don't know, maybe it's the first, maybe it's easier to see, is that we don't care about any of these segments that cross some point because they're already satisfied initially, so we can just ignore them. Okay, so now we have a bunch of these sections where each section is disjoint from all the others, and they're separated by these points. So we can do one DP here, which is like we can store DP for some section where there are like a couple possible ways that we might want to solve this section. We want to know if we're going to solve some section, we want to know this left endpoint and this right endpoint. Are these available for us to use? So let's say we're interested in this section here. If this right endpoint, if we've already moved it really far over to the right, then it's like it's not available. So we'll say it's like not where it needs to be. Because we might move it farther to the right, we might need to move it back. So if we've paid to move it back, well then we can use it, but otherwise we can't. So yeah, so the DP will store, for these left and right endpoints, we'll store like, do we have the left? And also, do we have the right? And then we also want to say, if we have these left and right endpoints, do we have to move the right back where it needs to be? And do we have to move the left back where it needs to be? So move left back. And then whether we need to move the right back. Yeah, so this will tell us for some section, if we know each of these conditions, right? If we know whether we have the left point, whether we have the right point, whether we have to be responsible for moving the left point back, and whether we have to be responsible for moving the right point back, we can pretty easily figure out what the answer to this is, right? So this will be the number of steps. So we can pre-compute this. For each one of these things, we can do it in log n time. I'm pretty sure you can actually do this in order 1, but log n does in fact pass. It definitely passes in C++, but it passes in Java too. Yeah, so we can calculate this in log n time. And we'll do this ahead of time. Okay, so once we've done this, now we can do a separate DP, which is kind of unrelated to this. And this DP stores DP for some section, and then whether we've used the left side, or whether like we still have the left side. And this will equal the minimum number of steps to finish. So in this case, the section is one of these 3 things here. I guess one of these 4 things. And we store whether this left point is in place. So we have a couple options when we do this. If the left point isn't in place, right? So let's say we're looking at this section here. If the left point isn't in place, that means the section to our left ended up using it and keeping it. So this point here, the one to our left ended up keeping it. So this means before we were to move it there, we can move it over here and then move it back. So we can do that. Alternatively, we can just not use the left point. So we can just, we just leave it on the left side. And these are kind of the same thing, but I handled them separately. I guess you could say, well, you'll move it over and back, but you'll just like not move it at all, right? And that's the same thing. So yeah, you can simplify your DP a little bit there. And also you can choose whether for this right point, you can choose whether you end up keeping the right point or whether you have to give the right point back to your next section. So yeah, you have two choices there as well. So this DP has like some constant transition, which is like order 4 or something, order 4, order 6. And this is if you don't have the left. If you do have the left, obviously you get to use and keep the left for free, because if your right person returned the left to you, then it's okay to leave the left endpoint within your section. So yeah, hopefully that made sense. I'll show the code for it pretty quick. So this is a mess because there are just so many parts. It's okay, yeah, 350 lines. But yeah, so the idea here, I'll go over the general idea. So this is the DP that I just talked about. And then I pre-comp for each of these things what the solution is. Okay, so this is a mask because the state is like several booleans. So I just store them in a bit mask for the state, which is messy. But yeah. I guess, okay, so I'll talk about my original solution. And then I'll talk about some of the optimizations I did to make it actually speed up in time. So yeah, we store all the points in some array, and then we have the 4 variables I talked about, which is the solution for each gap. So in the solution for gap part, let's read that first. So this we solve it for whether we have the left, have the right, need to return the left, need to return the right, where the left and right are, and then this array list of segments. So okay, so we get a tree set of all the left endpoints and all the right endpoints, and then if we just like have this here, this is just for sanity check. If we don't have a right, that means the left has to cover everything, and if we don't have a left, the right has to cover everything. So this is this part. And then we look at all of these interesting cut points. So these are the places that we might say, let's say you've got some series of segments that look like this. And then here's your left and here's your right. I switched colors on you, but hopefully this still makes sense. So what will happen is we'll have some cut point here, and then the left will handle all of the left endpoints to the left of this, and the right will handle all of the right endpoints to the right of this. Yeah, so it'll look something like this. And this is like the optimal way of doing it if this is your cut point. Now, in this case, we double counted this point here. So there's a better way of doing it. We can make a better cut point. Instead, we would make the cut point like this, for instance. And now the left would handle these, and the right would handle these. And that's like a better way of doing it. Strictly better solution. So yeah, so if we brute force the cut point, there will be some place where this will handle the optimal way. So we have all of these interesting query points. Now for each query point, yeah, we do what I said. So we find the first left endpoint going this way and the first right endpoint going this way. Okay. And that's it for this solve method. So this will give us this pre-comped array. We can say for each gap, for each of these variables, what's the answer? We can do that in constant time. All right, so then the DP is pretty easy. So it's a little caseworky, but not too bad. We either have the left or we don't, and then for each way we have some things we can do. So if we have the left, we can either keep the right or not. So this is if we do keep the right. In this case, the person to our right does not have their left because we have stolen. Otherwise, the person to the right does have it because we end up returning the right. And these call two different pre-comped values here. And then we have this other case here. Either we this is if we don't use the left, but really this is kind of unnecessary, I'm pretty sure. We can remove this transition entirely. So in this case, we use the left, and we need to either return the right element or not. But since this left element is used by our left kid, it ends up in our left kid, that means we have to pay double for moving it, because we have to move it to the right and then also move it back to the left. So this is why this return left is always true in this position. Okay, little hand wavy, kind of a long solution. Some optimizations that I did include in this solve method here, you don't need tree sets. You can make this an array and then binary search it, because you just add a bunch of things to it and then you query it a bunch. So you can just have an array with binary search. And then also, this is the same, even though this gets called for a bunch of different masks. So you can make it a little bit faster by building this outside of this array and then just passing it in. And then the other nice optimization is that some of these values aren't used, right? So you don't use all 16 combinations of these bits. In fact, have right is always true. And then there are probably other things you can speed up too, but here you don't actually need this variable because it's always true in every time that you actually use this. So you can remove some of this code, and then you can also, instead of this being 16 possible states, instead of it being 2 to the 4, you can make it 2 to the 3. Okay, yeah, that's all for problem F. It was a little tight on the time limit here, but I think it should be fine. Okay, sorry about the camera issues, and I'm just talking about blank screen here. Yeah, sorry about the camera issues. I'll try and figure it out again. I've looked at it in the past, but I'll try and figure it out. And thank you for watching. Hope you had a great contest. Hope your rating went up, and hopefully I don't fail system tests either. All right, see you soon.